Okay, so we ended last lecture by saying that if we want to write any single particle operator, we have to decide in which single particle base we want to represent it. And then write down two operators, a creation and annihilation. If this operator is the same operator as in the base, so it's just the number operator. We're just counting how many particles we have at that given state. If it's not an eigen vector of this base, no problem. So we have a creation at some value, annihilation in something else, and we have an amplitude. Okay, so far so good, but as I have said at the end of the previous lecture, that's still not a many particle operator. All these types of operators with two operators are basically single particle operators. The only thing that we take here into account is the statistics, meaning for fermions that we won't have more than one particle in this state. Okay, so how do we take into account our genuine many particle operator? Okay, so for that case we have more than two operators. Actually, we've seen already an example of such an operator when we did fields. And there we had a creation and annihilation of one type of particle or field, and then either a creation or an annihilation of another field. Therefore, three operators. Once we have an odd number of operators, what do we know? Without paying attention to what's the form and what are the meaning of these fields or particles, I know something about the system. What do I know? No conservation of particles. Because if I have an odd number, I can't have the same number of creation and annihilation. Therefore, I end up with less or more particles than I have begun with. Okay, so if I'm dealing with particles that are conserved, for example, the situation which is usually in condensed matter physics, let's say the number of electrons is conserved, just you can't annihilate or create more electrons than you started with, just because it's a low energy description of the system. Then I have to have an even number of operators, half of them creation, half of them annihilation. Okay, 4 operators, it's a two-particle interaction. Someone can explain why?
There is two creation operators.
Okay, what happens when we are looking on two particles? And I'll introduce here a Feynman diagram without explaining it, just as a cartoon.
You annihilate the two particles and then you create them after the interaction.
more or less, yes. What happens here? I have two particles to begin with. Let's say it's the easiest for this type of diagram. One of them comes at k, the other one comes at k prime. Now, they interact, and it could be a point interaction, then I will just show it schematically. And one of them will come out at k prime, k2 primes, k3 primes. So what do I have here? I started by creating two particles on the vacuum, or on whatever state I had there. Actually, it would be easier to write it this way. I annihilate two particles that come into the collision and create them a new at two different momenta, k numbers, and that's the interaction. That's exactly a two-body interaction. Could have something more complicated with 6 operators, then it would be a 3-body, 4-body, but usually, almost exclusively, we're dealing with two-particle interactions in most of physics. So basically, what we have to know, you'll have here an amplitude. Which tells me something about the probability of such an interaction. And once we have that, we know everything about the two-particle interaction. Okay, so let's go and see some specific examples. The simplest type of two-body operators, or even not the simplest, the general form, is I have a particle at Rm, I have a particle at Rn, and there's some interaction between them. Now, generally speaking, can exchange it and it will be the same operator. We'll use it for 0. Okay, what do I do with an operator? I use it on a vector. In this case, a many particle vector where I have n, capital N particles, and this is a state. One particle is at R1, another is at R2, and so on and so forth. So, another general thing I know about it is if I'm writing down the general two-particle operator, would be a sum over all states where I have some particle at Rn and another at Rm. Okay, and yn smaller than m.
Repetitions.
To avoid double counting, if I have interaction between n and m, I counted it already. I don't have to take from m to n. If I'm lazy and I don't want to think about it, okay, so I double counted and divided by half. So people use this formulation, whatever is more convenient for them. The only thing that is important here, no self-interaction. Okay. Very nice that I'm writing down an operator, but how does it actually look with our creation and annihilation operators? Because that's the only forms that we know to work with in many-body physics. Okay. I'm claiming, and in a moment I'll prove it, okay, half, just because I'm double counting. I'm going over all space, that's dr and dr prime. Creation operators at r and r prime. Annihilation at r prime and r. order is important because otherwise for fermions I'll get another minus here. And this is just a scalar that gives the classical interaction between points R and R prime. Yeah.
So this is the expectation value, it's not the operator.
No. This is an operator. If I'll sandwich it between this and its ket, then I'll get value. As I said, I'll prove it. So let's see how in general I can see what's going on here. And for simplicity, I don't want to write here's any specific interaction. I'll just look at the kernel of this operator, which is AR prime. Okay, and I want to see what it does to state some specific state where the particles are at R1, R2, so forth up to Rn. Okay. As I said in the beginning, I don't want to write exactly this wave function because I don't want to go to all the permutation and stuff. Therefore, and that you always do here, I want to write everything in operators. How do I transform this to an operator? Exactly, by creation operators at points R1, R2, and so on and so forth. So, I create this state out of the vacuum. The only thing that is important here to remember is I have to choose an order. I could choose the order, the opposite order, Rn, Rn minus 1, and so on. Here, it's not important. The only thing is be consistent. If you describe this in the following way, you can't in the middle exchange positions there. Each exchange for fermions gives you -1. You have to keep track of it. It's important. Okay. So I'm continuing from here. Sure. I had some vector of the n, capital N particles in the position description, right? I have a particle at R1, a particle at R2, a particle at R3, particle at R capital N. But if you remember a couple of lectures ago, if I'm writing it like down as single particle wave function, all the permutations, it's becoming bloated. It's becoming a huge expression with lots of permutations. And as I said, we never want to work with it. It's just too complicated. So, operators I know how to use. Because operators, I have very simple rules. All I have to know about them is, are they bosons, so they they obey commutation relations? Are they fermions? They obey anti-commutation relations. Okay, how do I write down a state where I have a particle at R1, R2, and so forth? I create particle at R1. I create a particle at R2, so on and so forth until R capital N. The only thing I said, the order is not important as long as you keep the same order during your calculation. You want to write this in this way, you can't in the middle change the positions. Okay? In a minute, I'll explain what we see here. Okay, so what do we have here? Sorry, one correction. Okay, let's look what happens here. I want to see what this annihilation operator does. Okay? What can it do? If R is not equal to R1, R2, R3, R4, and so on, it's just zero. You're trying to annihilate a particle that's not in that state. If you actually have a particle at R, meaning R is equal either to R1, R2, R3, and so forth. So, first of all, I have a delta function. I have a summation over all the positions. And if it's a boson, everything is good because nothing happens if you change the order of operators. If you have a fermion, I had to substitute it n-1 times to bring it before Rn. So that gives me this minus z, you remember, 1 for bosons doesn't make any difference. Minus 1 for fermions does make a difference. And I'm exchanging it n-1 times.
So it's not minus psi. It's
Oh, it's, sorry, just z. Okay. Questions? Yes, please.
רשמת שם Rn מינוס 1, Rn ועוד 1, ואז Rn אחריהם.
Too many indexes, but what can one do?
מה זה עכשיו?
n גדולה.
אוקיי.
Okay. You won't be too amazed that I'm going to do it for the next one, R prime. Same logic. The only thing that you should pay attention here it's -2 and not -1 for the simple reasons that one particle is already not zero. Okay. And I'm missing two terms here. add them. You see which terms I'm missing here?
Delta function.
The delta function and a dagger are in. Okay, so let's put it in. Okay. Yeah.
Why does M bigger than N?
Because I decided now not to split it for the case that M is before N and M is after N. I'll take, as I said in the beginning, sometimes I'm using this notation, sometimes there's a notation. Here it's more convenient instead of writing the two possibilities, because then you'll have once with n minus 2 and once with n minus 1. Just complicates life. Okay. Now all I have to do, these two guys, I want to push them back to their natural position. Here and here. Okay, what difference will it make? The only difference is that it will make is another factor which is exactly the same. Okay. So I end up here. Now, I can go back to the full operator. Now I'm writing down the expectation value. And okay. So I have the integral, I have the delta function, this is exactly the expectation value. If I have a particle at R1 and a particle at R2, whatever the interaction between them, and that's it. This now is already a number. All the operators already are out of the game. Okay, in general, any two-particle operator without regard to what basis it's dealing with would be okay, let's see a concrete example. Coulomb interactions between electrons. Okay, so let's write down the full Hamiltonian for a set of electrons where the single particle basis will be just the momentum basis, and see how it looks. So let's take the single particle basis for an electron that's in state K and spin either up or down. We didn't show where spin comes from here. Hopefully in 2 or 3 lectures we'll see where spin comes from. But okay, that's a total legitimate single particle basis. Here, the non-interacting Hamiltonian, the free electron Hamiltonian, we have seen already. Right, we just count how many particles we have at each momentum state K at spin either up or down, sum up everything, that's the Hamiltonian. Okay. Now we have an electron-electron interaction. Okay, looks innocent enough. Yeah.
איך האופרטור מגיע עכשיו לפני ה-A דאגרים? הוא לא אמור להיות בין ה-A דאגר ל-A?
This is a scalar. This is a number. The Coulomb interaction between position R and R prime. So the order here is not important. What you should pay attention actually is to this innocent looking index. Because all magnetic phenomena in condensed matter physics comes from this detail. What do I mean? If sigma prime is equal sigma, I have different commutation relations to the case where sigma prime is not equal to sigma. Why? Because the commutation between is always a delta of the quantum numbers. Here I have two quantum numbers, R and sigma. If sigma, and I have to sum up here, perhaps it's better to write it down explicitly. Both could be up, up, both could be down, down, up, down, down, up. All the situations might exist. Makes a hell of a difference.
זה בעצם סימול סימון.
Hmm?
זה בעצם סימון, אתה מסמן את הפוטנציאל בשתי וריאציות.
No, I could have interactions between two electrons with spin up.
כן.
Could have interactions between one of them up and down, down, up. All of them are legitimate states. It doesn't make any difference for the strength of the interaction, because if you're not taking into account magnetic interactions, just Coulomb interactions, it doesn't matter in what spin each electron is. But we'll see, either this lecture or the next one, that this actually creates magnetic interactions between electrons where you don't have an explicit magnetic term in the interaction. Someone could guess why? Physics, not mathematics now. Okay, the physics is the following. I have two electrons. Up, up. Could they sit in the same position?
No.
Could they sit in the same position?
Yes.
So the Coulomb interaction will behave differently for both states. Actually, if they're both up, Coulomb interaction is weaker because they never can sit on each other. For any one of you who knows something about atomic structure, either from chemistry or from optics, these are Hund rules. Doesn't say.
Never heard of it.
Okay, we'll get to it again, I think, next lecture, or even in your in the next session of the yes.
למה יש שם סכום באמת? זה לא אמור להיות אלקטרון יש לו מצב אחד או למעלה או למטה?
Well, yes, but you could ask exactly the same question here. Why do I integrate over all positions? The n electrons are at given positions, right? But I'm going through all the possible positions. Another thing that occurred here, I'm already thinking about a d-dimensional space, just because some of us don't live only on one dimension. Okay, so we have this term. We can do one of two things. Remain happily with this term and go change this term to R space, but since we chose to work here in K space, in momentum space, I'll have to do something with these operators. Okay, but we know exactly what one does in this situation. We know, we've seen it a couple of lectures ago. The only things that change from our 1D representation, it's here D over 2, and the dot here. Looks innocent, it complicates mathematics when we're dealing with situations above one dimension. Okay, but at the moment, all is good. Hopefully I have all the primes in space. Nothing beyond taking those four operators and writing their Fourier transform. Of course, each one of them has a different k-index.
לגבי האופרטור של עבדי, כאילו האופרטור, אז אתה מבדיל אותו?
Oh, that I forgot.
אבל גם כאילו שאלה בכללי, האופרטור זה כביכול אומר על הקשר.
No, this is not an operator.
לא, אני מדברת על זה האופרטור. אבל הוא מוגדר, זה הרי קשר בין שני אלקטרונים, נכון? אבל הוא מוגדר על ידי, על ה-VR פחות R פריים, שזה גם הקשר בין אלקטרונים. כאילו אני לא מצליחה להבין מה זה אומר האופרטור הזה, אם הוא מוגדר על ידי הקשר עצמו.
Well, let's go back to one particle operator. Okay, what do you have? The particle comes in at a given quantum number and comes out with a different one, right? And you have an amplitude for it. Here you have two particles that come in with two quantum numbers, k and k prime, sigma and sigma prime, and come out at q and q prime, sigma and sigma prime. Nothing happens to the spin. We didn't put in here explicitly any spin-dependent interaction. Okay? So, this is the operator part of it. This is just an amplitude. Okay, and what does it basically say? Look here in R space. Do I have a particle at R prime? Yes, that's a this is just a number operator, right? And after this has done whatever it has to do I have a particle at R? It's a two-particle operator. Basically, you look at the operator and it's like a cartoon. It tells you everything that you need to know here. Just what's the number of particles at R prime? What are the number of particles at R? And if there are particles at R and R prime, they have interactions between them. This could be the classical Coulomb, but could be anything else. And that's it. Looks heavy and very mathematical, as Feynman understood and gave us as a tool. You can represent it by cartoons. The actual calculations could be complicated, but understanding what happened here is very, very transparent, very, very clear. Okay, now you'll see that also in K-space you'll understand something very nice about it. Okay, so I have this monstrosity.
זה נראה שההנחה היא שהאינטראקציה משמרת ספין, אבל למה זה נכון?
Classical Coulomb interaction doesn't know about spin, right? So you, as I said before, you would think it means that spin is not important, right? As I said, you're in for a surprise. Spin is very important. I gave you intuition why. Okay, so we have this thing. The integrals at the moment could be difficult, but let's rewrite here one term. I want to perform the Am I allowed? Yes, sure, no problem. Just, I'm sorry that you can't do it in your notebook. You'll have to rewrite everything. I'll just, on the whiteboard, exchange where it's important. So, here I'll have R instead of R minus R prime. Okay. So what's nice about it, and sorry about it, I forgot this guy. Why are you so surprised?
Right there.
It's a derivative. prime here is a r here is a constant. Or it's better to write it the other way around. Okay, so let me rewrite what I have here. Okay, I just pulled out everything that depends on r before the integration on small r, which is these two terms. And v already doesn't depend on r. And I have this integral. What's nice about this integral? These guys don't depend on r. And this? What is this integral? A delta function.
שכחת את הסכומים.
Excuse me?
שכחת את הסכומים. יש שם עוד סכומים שצריך לשם.
The sum zone. And what do I call in physics this term? Not the mathematics, the physics. What does it express? What's the meaning of it?
שימור מומנטום.
Exactly, conservation of momentum. If I went in with two particles with momentum q and q prime, I come out with two particles that the sum of their momentum is equal to those that it went into the interaction. Coulomb interactions conserve momentum. So I can rewrite what's happening here as now I have a sum only on 3 momentums. Okay, just by putting in the delta function. And what else did I do? This is a definition of a Fourier transform. Okay. Now just one cosmetic massaging. I'll define Q as K minus Q. Because I go to infinity, it doesn't matter here anything. And what you're seeing here is the most famous Feynman diagram of interaction. I have 2 particles. They interact between themselves. This is a skew. And during the interactions, they exchanged a photon or momentum Q between them. I want to use photon because we didn't put in an electromagnetic. Yes, but you're right. That's. And this is just giving a mental picture of what's written here. Now, of course, you can have different probability for a small transfer of Q or a large transfer of Q. Depends on the potential. Okay, so let's calculate actually what is the Fourier transform of the Coulomb interaction. So we'll know what is the probability to transfer some value of Q. Okay, just wrote the Fourier transform. As usual in life, things that look very simple on the cartoon level, there are some subtleties in performing the calculation. First of all, if I'll go and try to perform it as it is, I'll have here divergences. So, first thing that I'm doing, I'm putting here an exponential cutoff. Hopefully we will be able to take this epsilon to 0 in the end or understand what it does here. Okay? This form is known as the Yukawa potential. Beyond what we're doing here, but just for general knowledge, field theory, if you replace epsilon by m, the mass of the particle that transfers the interaction, that's exactly what happens in nature. For electromagnetism, which is long range, epsilon is equal to 0, photons don't have mass. Fine. For other types of interactions that exist in nuclear physics, like the meson exchange, or if you want the weak interactions which have these W and Z exchange particles which have a finite mass, This will depend on mass and its short range. That explains, for example, why a nuclear has a finite radius. For the simple reason that interactions, as the nucleus becomes larger, there's less glue between them. There's a natural cutoff, and when the nucleus becomes too large, it breaks up to parts. Therefore, large nuclei are less stable just because there's no interactions between particles that are at the two ends of the nucleus. Okay. But here, at the moment, we're just doing a mathematical trick. It has no physical meaning. We're doing it just because we want to be able to calculate the integral. Okay. So I'm moving to spherical coordinates. Okay, from where is each term? No dependence on phi, so the integral over d phi is 2 pi. This is the r part, and this is the theta part. Jacobian, q dot r is qr cosine. I'm sure you've seen it somewhere before. So in condensed matter it appears often.
So you don't work in d dimensions anymore?
No, I'm back to our good old 3 dimensions. Although we have no convincing argument at the moment why 3. Okay. Well, 2 you can do by yourself. It's easy, and 1 dimensions I'll do explicitly, perhaps beginning of next lecture. Okay. This is cute. The usual motion for it, and okay. Okay, some straightforward integrals and putting in the limits. Just performing the integral on R here, I have no R dependence. It's a simple integral. You see what it helps here when I put in infinity, it's 0. And when I put in 0, I'm left with 1. And it's minus just because. Okay, so I rewrite it, just multiply it by the complex conjugate, get and if I'll take epsilon to 0, I'll have here a catastrophe. Because it tells me that the amplitude for Q equals 0 is infinity. What is the origin of this catastrophe? Someone can guess? Very simple, actually. The Hamiltonian of the systems that I wrote in the beginning is unstable. If I throw in capital N electrons into a system, what will they try to do? To run away to infinity. So that's actually what this divergence tells me. You wrote something that is unstable. The energy here diverges. How can you correct it? Well, the easiest way to correct it, we're going back to our good old friend Thomson. When Thomson thought that he has this, what it was called, plum pudding or raisin pudding for an atom, he thought there's n electrons in the atom, but n electrons in the atom will just run away. You put in a positive gallium. That is the simplest solution to the problem. The true solution is, of course, to put in the positive ions of the underlying lattice that compose the material and treat it, but no one wants to get into this complication to add another particle, these positive ions, and therefore what we will do in the beginning of next lecture is just see how simple assumptions about a positive background will solve our problem. But it just shows you that if you neglect some detail, it will come back to bite you. We forgot about the fact that when we're writing down the Hamiltonian with Coulomb interaction, it's not stable, and it returned to us as a divergence. Okay, questions? Yeah.
לא הבנתי את הבעיה במשוואה. אם Q שווה 0 אז זה בעיה?
If epsilon is equal to 0, as should be because this we just stuck by hand, right? And Q goes to 0, we have a divergence here.
מה זה Q? Q זה המינוס של המומנטומים שלהם.
Tells you that you always have an infinite contribution from the Coulomb interaction. Why do you always have an infinite contribution? Because these particles, no matter how far they are from each other, it's still not far enough. If nothing holds them here, they'll want to continue and escape.
But how do you see the connection to the distance here? It's the momentum.
Okay, that's the good old rule of thumbs about Fourier transform. Small q's,
Big R's.
large distances. Same as small frequencies, large times. Since we did here basically a Fourier transform, that's the meaning of it. Okay, so we'll stop here and see how we actually correct this next.